Thank you. I would like also to thank the organizer for being here. Indeed, in this talk, I'm going to present a model which has been developed with Carlo Baranghi in order to interpret some recent experiments which were quite puzzling. And in this experiment, the spectrum of vortex line density was measured in a turbulent superfluid. And since the measurement was done in the inertial range, we expected to find the same behavior as the one found in classical viscous Navier-Stokes turbulence, but we didn't. So the model is an attempt to understand this. So this is so already two people talked about superfluid turbulence. So this overview is very short. What I just want to point is that our interest is in very high Reynolds number flow, larger than R lambda, larger than 1,000, closer to 2,000. And we're interested in flow geometries which have a classical counterpart. So we're interested in jets, grid flow, but not in the exotic flows that one can make with a superfluid, like counterflows. You are trying to interpret experiment done with helium-4 above 1K. So since it's helium-4, it means that the vortex core size is about 1 angstrom, as said by Motoko before. And the typical size of the experiment is centimeters. So the vortex are really lines. And since we are working on data above 1K, that means that there is, on top of a superfluid, there's this normal fluid. So even if you only have a fraction of it, a few percent of normal fluid, that means that you have some viscosity and you have a dissipation process in the fluid. So you don't have to face all these issues about how the energy is being dissipated at low scales. So the present understanding of superfluid turbulence, as already explained before, is mostly due to Joe Vinan. And it states that the normal fluid is fully coupled to the superfluid in the inertial range, and that in the inertial range, you expect the superfluid to have a Kolmogorov-like cascade. And this result, this model, this theory is Giovannian theory is based upon a very few results and only one measurement of a local fluctuation in space and time in a fluid. So it was a liquid helium von Karman flow. Above the superfluid transition, the velocity spectrum, which is plotted here, the velocity spectrum exhibits scaling which is compatible with the Venus-Pfeiffer power law, and below the superfluid transition, it stays the same scaling. So, and last year, this experiment was, some measurements were published in which the power spectrum of the vortex line density was presented. And on this plot, as a function of frequency, you can see without any flow, the noise baseline. And when you increase the velocity and you increase the Reynolds number, there seems to have a power law which is compatible with the Venus-Pfeiffer. So it is the most generally admitted ideas is that vortex line density can be think as superfluid entropy, vorticity, and one doesn't expect the entropy in a classical fluid to scale like a Venus-Pfeiffer power law. So that was unexpected, and this is the puzzle that we try to address. So this work was, this measurement were done in collaboration between several institutes and laboratories in. I have just two slides saying how was done the experiment. There's a liquid helium wind tunnel. The size typically here is 10 to 20 centimeters. And there's a liquid helium flow going up, and it is being probed by several probes, velocity probe, cold wire, and a vortex line density probe. So those vortex line density probes are based on the fact that in a superfluid, you can propagate temperature wave. This is called second sound wave. and these temperature waves are being attenuated by the vortex line. So if you measure the attenuation, you can go back to the vortex line, and if the probe is very small, like it is the case here, it is a macro machine probe. If the probe is very small, you have the vortex line density locally and as a function of time. This is just about the experiment. If the experiment, the probe is a small resonator. There's a second sound wave, standing wave in it. If you look at the first mode of the second sound standing wave, without any flow, you have the blue curve, which show the different, well, sorry. This is the frequency response of a probe. If you look at the resonance of the first mode here, without any flow, you have some attenuation. And if you put some flow, you have more attenuation. And if you stand here and you measure as a function of time what is the attenuation, you get as a function of time vortex line density. And just one other piece of information which is relevant here is that these kind of probes are not able to measure vortex line which are pointing in the direction of propagation of a wave. So it is an anisotropic probe, and vorticity is only measured in two dimensions. So we try to compare to some classical. If you look at some classical counterpart of this measurement, Zhu and his collaborators measure the spine-wise vorticity component in a grid flow and in a wake flow using a 4-wire vorticity probe. So the probe is appear here. And this is the power spectrum of one component of a vorticity. So it is not exactly what we are measuring in liquid helium, but still, it is interesting to see that when you increase the Reynolds number here, in this region, in the low K region, the spectrum looks rather flat or slowly decreasing. And in the same paper, this paper, they present data up to Reynolds number 274, and you still have the same tendency. The spectrum is flat or slowly decreasing here. So to get a more closer comparison between measurement in superfluid and classical fluid, Professor Kaneda and his group were kind enough to provide us with a vorticity field from their simulation with 2048 resolution. And what is nice about this DNS data is that we have the three components of a vorticity field, so we can reconstruct exactly what would be the quantity that we are measuring in superfluid helium. So the kind of vorticity in the plane, projected vorticity. So this power spectrum, the curve in red shows the result of a DNS simulation. The inertial range is here, and in this region you see again that the tendency or the scaling or whatever the physics here in the classical fluid seems to differ from the slope that was measured in superfluid helium. So this fit in superfluid helium, you should only look at the slope of it, not the position here. We just put it here to see. So superfluid, the entropy spectrum in superfluid seems to be different from the entropy spectrum in the classical fluid. And this is the problem that we wanted to address with a model. So we wanted to reconcile the classical model of turbulence, superfluid turbulence, and this anomalous spectrum. So to try to understand what can make the difference between these two kinds of turbulence, we go back to what makes superfluid turbulence specific. So for example, when you have vortex interacting, it is well known that you have some generation of vortex loop, for example. And in this simulation by the group of Tsubota, these vortex loops are generated in this region. And since there's no vortex here, they evaporate, and we can clearly see them. But they're always present below that. So when you think of a vortex loop, it has a lot of entropy or vortex line contribution, but it has a little effect on the far field because it is a dipolar source of velocity. And Kelvin waves have been addressed already several times in previous talks. When you have vortex interacting and this generation of kinks and Kelvin waves and whatever along the vortex line, here again, it's a process in which a lot of entropy is produced, but which doesn't change a lot the velocity field at low k. So, and these two ingredients okay, this is a numerical simulation of a vortex tangle in which vortex bundles are evidenced, and they, according to the author, they correspond to coherent structures in the fluid. And you can see that when these coherent structures interact, and this is a recent result by those authors, when we see this bundle interacting again, you have generation of entropy at small entropy and small scale features. So the idea was to say, if you think of a vortex tangle and you look at it locally, you can identify some structures like loops, anti-parallel vortex, randomly oriented vortices, which generate a very small velocity field far away from it. But so we want to decompose the vortex tangle into two contributions. One in which we put all these unpolarized structures, and the other one in which we put the mean polarization of the box. So this can be done precisely and rigorously by coarse graining procedure, in which we define the polarization in the box, looking at the average of all the vortex line, and from this we can define the vorticity, and to this vorticity we can associate a vortex line effective vortex line density. And on the other side, for the unpolarized field, we can also find what is going to be is vortex line density, taking the vortex line density of the initial box minus the one which has been defined here. And so the main idea of the model was to say this polarized field is going to contain all the energy to control all the velocity fluctuation in the inertial range, and it is the field which is described by by Vinen's model. On the other side, you also have this field contains most of the entropy, and as I will try to justify, this entropy is mostly passive. So, and we know that passive field obeys the -5/3 power law in their spectrum. So this decomposition, if we can justify it, is able to explain the -5/3 power law, the passive spectrum power law. So now what I have to do is to justify these 3 points. So the easiest one is this unpolarized field really passive? So we want to know two things. Is these structures are going to produce some velocity far away from them? And this is unlikely since they have no mean polarization. So you can see a dipolar or multipolar source of velocity field. And on the other hand, we want to check that if this vortex line in this unpolarized field, is it transported by the flow? So since we assume that the flow is incompressible, when we stretch and pull and this fluid element So the total vortex line is conserved. So we have some ingredients we can justify that the unpolarized fields behave as a passive field, to some extent, of course. Now we want to make sure that the energy is in the polarized field. So the total mechanical or kinematic energy of the flow was measured, because there was a pitot tube in this experiment. So we know how much kinematic energy there is in the flow. Now we can estimate what is the kinematic energy which is in the unpolarized field. So this procedure is rather standard, in fact, but just to remind it, if you take a single vortex, you look at the velocity field around it, it can be estimated with Birte-Savart law. And if you integrate the kinematic energy along a vortex of unit length from the core size to some cutoff scale B, you can get some kinematic energy. So for the core size, we take 1 angstrom, and for the distance on which we integrate, we go to the next vortex. So the B is taken as the intervortex spacing, and this intervortex spacing can be estimated from the measured vortex line density in the fluid. So we can put numbers in that, and we get the kinetic energy per unit length for vortex line, and then we multiply by the total vortex line density, and we can have an estimate of the kinematic energy in the unpolarized field. And when we compare this energy to the total energy, it is 2 decades smaller. So that means that indeed the energy seems to be concentrated in the polarized field only. And now we want to check that the entropy is in the unpolarized field. So we have the same procedure to do that. On one side, we know the total entropy of the fluid, because it is what is being measured. And we want to show that the entropy of the polarized field has a contribution on this plot which is significantly lower than the measured values. So to do that, we are going to make a few assumptions. They are detailed in the paper, so this is going to be a bit fast. First is that we assume that the polarized field behaves like classical turbulence. Now we have to put on the paper all the information we know about the polarized field. We know all the kinematic energy injected in the fluid, from which we can infer the vorticity of this polarized field, mean vorticity. We can estimate by several means what is the smallest scale in the flow. So there are a lot of this has been addressed by Sergei Nazarenko in Sergei Nazarenko's talk. There are several ways of estimating what is the cutoff scale in this turbulent flow, but they all end up giving the same kind of numbers, typically in this experiment about 1 micron. So now we have to make some assumptions about the power spectrum density of this entropy, the classical turbulence. And we have a first order model stating that it is flat. It is not too far away from the DNS experiment as the first order approximation. So it is flat till the cutoff scale. So now when you put all these things together, we find in fact it's an upper bound for the spectral density of a polarized field. And this quantity is lower, is around here, so it's lower than the measured spectrum. So this is showing, at least strongly suggesting, that the entropy is concentrated in the unpolarized field. So this interpretation is consistent with all the data we have on the experiment. It is, of course, preliminary, but it allows to explain the anomalous spectrum of entropy. And so just to summarize the two main features, the unpolarized field has passive features and contains most of the entropy, at least in the upper inertial range. And the polarized field mimics a classical fluid and contains most of the energy. So this seems to be consistent. So now we've been thinking about how to validate the model and how to disapprove it. And there's different playing ground that can be imaginated, but two of them are two experiments which are being one done and the other one being designed in Grenoble. So I would like to finish with an advertisement of these two experiments. So the first experiment is called TSF, superfluid turbulence, something like that. It is done by a lot of institutions here. It's a very wide collaboration. And liquid helium fridge is dedicated to this experiment. It's a huge one. To give you an idea, the power consumption of it is about 1 megawatt. To cool down the experiment, we need 2 months, something like 2 months. To warm it up, also 1 month. And it takes several engineers to run the experiment, so it's a really huge experiment. And we have a closed loop of liquid helium, which can be both classical or superfluid. The mass flow rate is 700 grams per second, which is the highest ever achieved with the superfluid. And in this loop is inserted the test section in which there's a grid flow. So this is flow conditioning, there's a grid, and downstream there's a set of probes which are used to measure the properties of either classical or superfluid flow. So the range of temperature is here, and the air lambda goes up to 350. So what is nice about this grid, because it's very well known, and the turbulence is clean, is isotropic, homogeneous. So that means that we can have precise estimation of what would be the entropy in the classical fluid. So then we can compare it to the entropy measured in the superfluid. And after 3 to 4 years of effort, we last spring we were able to measure the attenuation of a second sound standing wave, from which we will be able, after calibration, which can take a few months, we're going to be able to infer what is the mean entropy of a superfluid in this experiment in a wide range of parameters, temperature and velocity, and Reynolds. And to finish with this slide, this is a project which is being prepared also in Grenoble. This is the helium fridge, which I just mentioned. It is going to be connected to a big tank. So this tank is being, this summer was installed and painted. And inside this tank, if we get the funding for, we want to put a von Karman flow of liquid helium, which size is going to be, depending on how many money we get, but about 60 centimeters to 50, 70 centimeters inside. So this is going to produce very large Reynolds number, but more important, it's going to have large scales. And this is very convenient if you want to measure fluctuation, because probes are never very small. If you make a probe which is 0.1 millimeter, you are happy. So if a large scale is 10 centimeters, that gives you a lot of inertial range. So, okay, I think I catch up with the time. Thank you.
Questions?
So what is wrong with the simple argument that the entropy spectrum is just k squared multiplied by the energy spectrum?
I don't want to go in this ground. It's too sleepy. I don't know. I don't know, but it seems to be consistent with, it doesn't seem to be consistent with experiment and DNS, at least up to R lambda 500.
Non-smooth field, you cannot differentiate it.
only for small scale.
I mean, maybe you have an explanation for this, and maybe I need to think about this some more. But your assumption about being able to represent the vortex lines as passive scalars neglects two facts. One is that vorticity will stretch. I mean, it'll stretch in a superfluid just like it'll stretch in a classical fluid. And therefore, the vortex line length can grow locally, maybe not globally, but locally. And then the second thing is that the reverse process has to be happening, because in the decay, what you're measuring is the vortex line length is decreasing, and therefore you have potentially both a production mechanism and a depletion mechanism. Now, these both might be happening at such small scales that it really doesn't affect what you're measuring at intermediate scales at all. I mean, there could be
Okay.
simple
Yeah, I agree with your second point, and the first one I'm not sure. For the second point, indeed, we have a mechanism of continuous production of entropy at small scale and also attenuation at small scale. So there is a balance. What I just wrote, maybe I didn't say it properly, but I'm sure I wrote it, is we have some features of passive field. We have some features, not all of them, and there's many ways of having a passive field, of defining a passive field, and most of them, to the best of my knowledge, they end up with a -5 Hz spectrum. So, but for the first point, it is there's something which is very different when you think of stretching of superfluid tangle between inertial range and small scales. If you imagine a tangle, a bundle of vortex, all aligned in the same direction, and quantized vortex, superfluid vortex. If you take this object and you stretch it, you are going to increase the vorticity the same way as it happens in classical fluid. But so this probably happens the same way in classical fluid and superfluid in the inertial range. But if you go to small scales, where the production of entropy occurs, then you don't make it more intense by stretching it. You can surely stretch vortex, but since it's quantized, it doesn't get more intense. So there's qualitatively something which is fundamentally different between this classical and superfluid. That's why it's...
We can discuss that.
Yeah, but it is a preliminary model, and it can surely be improved. But I think there's a good reason for which vorticity can be passive because of this. Although it might be shocking, this could justify it.
If there are no other questions, let's short break. We have to reconvene at